we come now to Lisa Nicolina, also from my group at Nanogune, and also involved in the Peter project. And Lisa is actually involved in the profabrication, and she will talk about various aspects of the profabrication. So Lisa, please.
Hello, everybody. Thank you, Rainer, for your kind introduction, and welcome to my talk, Probe Fabrication for Ultrasensitive Terahertz Nanoscopy. In my talk, I will talk mostly about focused ion beam fabrication of terahertz near-field probes, and I will show you how we optimize the probes parameters such as length and apex in order to get high resolution and high enough signal. As you know, terahertz range lays in between infrared and microwave, and terahertz radiation is highly sensitive to molecular vibration, molecular rotation, to semiconductor properties. That makes it applicable in such areas as biology, medicine, pharmacy, as well as in information and communication technology. But the main drawback of terahertz radiation is poor resolution, which is about from 50 to 500 microns. In order to overcome this limitation, in terahertz S-norm metallic IFM chips are used. So the metallic IFM chip is illuminated by a laser focus beam, and in this case the chip acts as an antenna focusing the illumination at its apex. As a result of this process, we can improve the resolution of terahertz up to 3 orders of magnitude, from several tens or even hundreds of microns to several tens of nanometers, what is actually the size of the chip. The antenna performance of the chip very much depends on its length. So for our range, which is about 3 terahertz, or with a wavelength of 100 microns, the antenna has to be quite long. So here on the right-hand side, you can see the image of our homemade chip, which has the length about more than 50 micron. So it's half of wavelengths of our terahertz frequency. Unfortunately, the standard alpha metallized chips, they are far too short to be a good antennas, having the length of 20 microns. And in my talk, I will show you how we fabricate those chips having a good antenna properties. A quick look to the lab. So we use a focused ion beam technique. Our machine is a Helios 450, equipped with an electron beam column, ion beam column, a micromanipulator, and some GIS systems. They are pretty much standard instruments for FIB, and all these instruments we will use for the fabrication of our chips that I show you later. So we fabricate fully metallic platinum iridium probes. For this, we use commercially available platinum 80 iridium 20 wire. Here on the left-hand side, you see the image of this wire of diameter of 125 micron from Advent. And with yellow, I colored the pre-shaped chips. They are pre-shaped and sharp, having the length of about some tens of microns, and apex is about 100 of nanometers. As a support for our chips, we use standard silicon cantilevers from Nanovolt. They don't need to be new or clean, because the tip itself is cut away in order to prepare the place where we put our tip. So now having the tip and the support, we have to transfer the tip to the support. How we do it? We do it by using the micromanipulator, here colored in violet. The micromanipulator is a standard tool in a FIB, and typically it's used for lamella preparation in order to transfer the lamella from the sample to its copper semicircle support. And we use the micromanipulator to transfer the tip to the support. We inject the micromanipulator to the chamber and gently put it, bring it close to the tip. We glue it with a platinum FIBIT process. I will show you later what is this. And we cut it by ion beam at the desired length. Here is about 30 micron. So for those of you, or I put it for the audience, because maybe many of you are not so familiar with FIB, so I wanted to show the overview of this process, how we glue our tip to the micromanipulator or later to the cantilever. So to glue the tip, we deposit some platinum. How we do it? For the platinum, we need some metal organic precursor, which gets volatile when it's hit inside the GIS system. So those molecules are injected with the GIS system into the chamber of the microscope, and the molecules are adsorbed from the surface. Once we scan some area of the surface, either with electron or ion beam, we get some secondary electrons coming out from this particular area. And those electrons lead to the dissociation of those metal organic molecules. By the way, for the platinum, we use a trimethyl platinum 4 molecules consisting of platinum, carbon, and hydrogen. So after dissociation, we get a platinum deposit and some volatile products. This is how we glue our tip to the micromanipulator and later to the tip. So having the tip on the micromanipulator, we can put it on a silicon cantilever. We put it exactly to the place where we want, what we prepared in silicon cantilever. And we glue the tip on the sides with the same platinum FIBIT process. Then we cut away the micromanipulator, and then again I glue the tip as good as possible because it gets it more stable. So here you can see the ready tip glued on the silicon support, nicely fixed everywhere. And at the end of the fabrication process, I check again the apex, because especially for the very sharp tips with the apexes below 50, sorry, this is below 50 nanometers, it could be that there is some occasional deposition on the apex or some dots, so the apex has to be checked again at the very end of the process to be sure that it's in a good condition. Following this FIBIT fabrication, we could get the tips with the lenses from 15 to 80 micron, and with the apexes from 30 to 100 nanometer for this particular material, platinum 80, iridium 20. And now I will show you a couple of works of my colleagues where those tips were used. As you remember from the introduction, the length of the tip is a very important parameter. So the tip having the length of half of wavelength, having the good resonance properties. The aim of this work was to find the resonant length of the tips. To do this, 6 tips were fabricated using those methods I just showed you. the tips having the length from 70 micron to around 80 micron. Those tips were used to measure the photocurrent on a terahertz photodetector. Basically, in this case, the measured photocurrent was proportional to tip efficiency. Here I draw the terahertz photodetector consisting of a graphene layer encapsulated in between two HBNs. And those are on top of two laterally separated gold contacts. Once we apply different voltages on those gold contacts, we create a so-called PN junction in graphene. And once we put the tip close to PN junction, due to thermoelectric effect, photocurrent is created. This has been nicely explained yesterday by Tobias Kamprad. And we measure this created photocurrent with those with the other contacts. On this image, you can see the measured photocurrent values depending on antenna length. It has been found that a numerical simulation of near field intensities via the antenna length has exactly the same trend as our measurements. So we could conclude that Folkmate tips do support terahertz antenna resonances, and the resonant probes provide up to 9-fold signal enhancement compared to a standard RFM tips. I want to mention here that in this experiment, the apex of the tip, the apexes of the tips were kept the same, around 50 nanometers. And now in the second work, and the aim of this work was to find how the apex of the tips influence of terahertz near field signal. To understand this, standard commercially available tips were used. One from a nanovolt having the apex radius 25 nanometer, covered with the platinum iridium. And the other three tips were from Nanotech, having the radius from 250 to 750. Those three tips were golden tips. So we have measured terahertz SNOM line scans across the sample, which is a hard disk read-write head, having the flat topography and a sharp boundary between metal and dielectric parts. On this graph, you can see those line scans we measured with different tips, and we see that the signal drops significantly down when the apex of the tips is small, especially for the metallic part. The signal dropped down by a factor of 50, and on a dielectric part on factor of 7. Although the signal drops down for the sharp tips, the absolute resolution is, of course, higher for the sharp tips. So we could conclude that sharp tips give us a low signal, although high resolution. To have both things, to have high resolution and high enough signal, we have to use sharp tip, but a resonant one. To push the resolution as far as possible at terahertz frequency, we fabricated with FIP technique a super sharp resonant tungsten tip, having the apex of 6 nanometer and the length of 40 micron. Using the same sample as I showed you a slide before, we measured the line scan, And we found out that the resolution what we could get is 13 nanometer at 2.52 terahertz, what is at the moment the world record for this frequency. And this brings me to the end of my talk. I hope I convince you that FIP technique allows us to fabricate the tips precisely controlling the lens and the apex. And with those homemade tips, we could get unprecedented resolution of 30 nanometer at terahertz frequency. I want to thank all NanoOptics group, especially our boss, Rainer Hillebrand, our theoreticians, Alexey Nikitin and Sasha Gavedinov. He will give a talk after me. Thank you, Stefan Mastel. He is around here in this workshop, and Kurlin Mazen and Shu Chen. And thank you for your attention.
Thank you very much, Lisa, for the talk. Are there questions? Again, if you have a question, you can just ask.
Lisa, does the residue of the platinum when you're using the manipulator affect the tip performance, or is there do you have to remove that at the end?
Yes, I remove it at the end because, well, it has to be removed. Otherwise, the tip will be glued to the micromanipulator. No, but we need to separate it. The platinum that you used for the glue, does that residue on the tip become an issue? Or yeah. I understood what you asked. You mean this patch, the rest of the platinum? Yes. Well, it's actually unnecessary to remove it completely, but sometimes yes. Well, if I cut the micromanipulator somewhere here, I have the rest of the micromanipulator and the platinum, and then at the end of the process, I just clean it away again. It's not a problem with electron or with the ion beam. Thank you.
No more questions? Sasha?
Thanks, Lisa. Very good talk. Quick question. How reproducible are the tips?
You mean lens or the lenses or the axis?
I guess the performance depends on both, right? So it should be both the length and the tip apex radius.
Yes.
Can you make two similar tips?
Two similar tips, yes. Well, with some minor difference. They will be not exactly the same, of course, but sure. I can control both the lens and the size of the apex.
I see.
I would say the size of the apex I could control in the range of 10 nanometers or less.
That's good. That's good. And when you look at the tips, do you put a layer of carbon on them? Does it contaminate them? Because you said that you need to look at the apex verified.
Yes, a little bit it contaminates, but I try to do it as fast as possible.
Okay, thank you.
Or I sharp it like blind without scanning with electron beam.